So now we're going to be talking about the harmonic oscillator again. So we haven't really finished the harmonic oscillator. What I want to do now is I want to go into looking at the Hamiltonian for this harmonic oscillator. So we've sort of established before that we have these raising and lowering operators, and these raising and lowering operators are basically these variables that can help us recast the harmonic oscillator model in a different way. That's really all they do as far as we could tell right now. And what we're going to see is that these raising and lowering operators, when we apply them to the energy or the Hamiltonian, for example, we're going to get some interesting properties regarding raising and lowering that energy. So by merely defining some variables that sort of fit nicely into the harmonic oscillator to make it just look different, we are able to then see that these are integrally, or I don't know what word I'm looking for, but they're important when it comes to putting them in the context of the Hamiltonian or the energy of the oscillator, right? So if you remember also, before we get into this, is that the energy or a harmonic oscillator is something that just oscillates, right? The reason it's called, there's sort of semantic reasons as to why we call it the harmonic oscillator, but again, it's just a model that explains the motion of some oscillator, right? We've had a differential equation initially sort of describe how this harmonic oscillator behaves, right? And that was the Schrodinger equation plus some potential function, right? You have the Schrodinger equation plus the potential. If we have the potential take the form of a harmonic oscillator, then we can redefine. What we did is we defined some variables. We put those variables into our harmonic oscillator model, cast it out by the Schrodinger equation, and we went from there. We restructured the harmonic oscillator formula. Now what we're going to do is we're going to take a look at how these commute with the energy, right? So let's get right into this. We have this is our energy, right? So the Hamiltonian is the energy, and this is one of our variables. And we have to also keep in mind that these variables are complex conjugates of each other, right? That's important. So we have one of these variables, and we want to find what the commutation relationship is between this variable and the Hamiltonian, right? So this is by definition what the commutator is, right? And we just go from here, right? So we have our Hamiltonian, right? This is what we established initially in our previous video. And the same Hamiltonian right here, right? And then we have our two A's, these two, this variable right here, right? So all we're doing now is just algebra. So when we get down to this point here, we're kind of just multiplying, bringing these A's inward, right? These variables inward, right? So we have this one right here, and we have this one coming out in front here, right? And then we're distributing this negative sign also. And when we distribute the negative sign, we see that these two guys will cancel out, right? So that will cancel with that, okay? And then what we get is, if I get my pointer again, we could factor out these latter A's, right? So this one here was right here, right? But this one here goes in front because we're in front here. But so this latter A will factor out in the back here, just like we did with these two. So this A here is this one and this one, right? If you follow me there. And then what we find here is that this is just a commutation relationship, right? There it is. And if we recall that the commutation relationship between these two operators, well, that's just -1, right? So we get this. So we see that when we commute the energy or the Hamiltonian with one of these variables, we get this interesting relationship back, right? Similarly, we can go through the same process and get this relationship. So what do we have, right? So sort of summing up from the previous video and sort of summing up from what we have right now is that we define these complex conjugated variables, right? We arbitrarily say, you know, let's make this equal this whole thing, and then let's make this one equal the same thing, just complex conjugated, and let's see what happens, right? What happens is that we get these relationships and these relationships, okay? When they're applied again to the Schrodinger equation with that potential function that matches a harmonic oscillator model, right? So that's what we have so far. So I'm just going to reiterate. I'm sort of big into reiterating just so we can like really get this understanding into our head, because this is going to be essential for us moving on into talking about quantum fields, right? So we have these relationships here, right? So the Hamiltonian, this is with the Hamiltonian, these are the variables, and these are the relationships between the two variables, okay? Now, let's take a look now at how these are physically relevant, right? So these are physically relevant. Let's see here. When we start to consider the Hamiltonian, again, acting on this, right? So what is this? This is an energy. This is the energy of some particle, say. And we're acting on that energy with this operator, right? So this operator, what can we do here? Well, we can multiply, right, this with this, okay? That's right here. This is just adding nothing, right? Because we have the minus or the negative of this and the positive of this, of the same thing. So we've essentially added nothing. But this is a very nice trick in sort of every domain of physics where you can do this, right? You can add nothing, right? Or you can multiply by 1, right? Multiplying by 1 would be, say, like multiplying by AH divided by AH, right? So, and then we'll come across that stuff later. But again, this is really just, we're adding nothing to this, right? Because this is the negative form of this one, right? So these two guys here, that amounts to 0, okay? Again, that's just a nifty trick, nifty math trick. Now, what we can do is we could say, well, we've added nothing, right? That means, well, but this here, that's just a commutation relationship, right? Then we have this right here. Okay, so let's keep on going. We've said that this commutation relationship is right here, right? We've established that in the past, or over here, right? Right here, okay? And then we're carrying this down here, we're carrying these down, and then what we can do, you know, I realized now that we have an A missing, so I'll just squeeze in an A right here, an A right here, but we could see, right, we have A's all over the place, these A operators. We can essentially cancel them out because we have one right here on one side of the equation, and then we have these here on the other side of the equation. They're all the same thing, right? So we divide everything by A, essentially, and we get us this, okay? What does this mean, right? So when we apply the Hamiltonian and this operator, we get an energy minus some quanta, right? What do I mean by quanta? Well, this is just Planck's constant, right? A very small number, just a number though. This is the frequency that's associated with our energy, right? So what this means is that when we operate on this state, what we get is the value of that state, the eigenvalue of that state back minus just a little bit, right? So that's something lower than E1, E0, say, right? That now we're able to see that this A, this variable that we really just arbitrarily defined in the last video, is a lowering operator. It lowers the energy of your harmonic oscillating system, right? Similarly, we can go through the same rigorous mathematical tools that we've used up here to get to this conclusion right here, right? So this conclusion right here is that when we have the energy, or when we apply the Hamiltonian and this other operator, the complex conjugate of what we did up here, right, we just get an addition of some unit of energy, right? And that is, therefore we call this a raising operators, or sometimes they're called annihilation and creation operators, right? Where these are the operators that sort of deal with the particles, right? So that you have a particle of some energy, and the way it is going to gain energy is mathematically is through these raising and lowering operators, right? And what's going to be interesting as we progress on into quantum field theory is that the relationships between these raising and lowering operators are going to be the backbone, the essential tools on how we define these fields, right? These fields are going to be defined, right? We can define them in terms of what kind of mathematical objects they are made up of, right? Spinor fields, tensor fields, scalar fields, vector fields. We can define them that way. We can also, but again, so the vector fields say at each point represents some particle, right? But then how you excite each particle to different energy levels is going to be these guys right here. And these guys are going to have unique relationships with one another when it comes to talking about what kind of field we are looking at, right? So each field, again, has its own mathematical object that we are interested in, right? We have, say, a vector field or a scalar field. But associated with that is going to be these operators that sort of dictate the dynamics of the energy of the field. And that's another way we can define these fields. And we want to know what these are, right? We want to know what these are because essentially when it comes down to it, we're measuring energies, we're measuring momenta. We're not really concerned with the actual, we kind of are concerned with the actual mathematical objects, but the things that we measure in the lab, for example, are the energies, how the energies fluctuate. And so the energy fluctuates, again, by means of these raising and lowering operators, or creation and annihilation operators, right? So the lowering operators, these are going to be annihilation operators also. That's another name for them. And these are also creation operators. Okay. So we have these creation operators, these lowering operators, and all this stuff. We have projection operators. We're going to look at other types of operators in the future, but the operators are sort of where it's at, right? Because those are sort of the things that manifest energies, right? They excite energies, they lower energies, and what we, at the end of the day, want to measure is energies or momenta. Let's quickly talk about the number operator. The number operator is interesting because so we have these relationships right here, okay? And these are sort of arbitrary, right? But let's take a look at what happens when we make these arbitrary, or when we make these rules here. So say we have a dagger in A acting on some state N, right? This could be an energy state, it could be a momenta state. And what we want to do, what we're going to say is that we're going to say that this is equal to this. Now let's just see what happens, right? So, or not equal to this, sorry. So we're going to set these two, we're going to say that these are just the way they are, right? And let's see what happens. So what happens when we act on, first with A on N? Okay, well, if we act with A on N, we get square root of N times the state, the next lower state, right? So that's right here. Now, then we act with a dagger, right? So here's our a dagger. We're acting on, well, when we act on a dagger, we're raising that back up, right? So we call this a lowering operator, so because we said it right here. So let's just say this lowers n to n minus 1. So if we're acting on n minus 1 with this with the creation operator, we're going back up to n, right? So that's what I have depicted here, right? Say n equals 1, right? And say n equals 2, right? So what we did was we lowered down to 1, and then with a dagger, we went back up to 2, right? So we're going back up to 2, right? So in this case, we just went back up to n. We went to n minus 1, back to n, right? And if we use this rule here, this was n minus 1, this was n minus 1, so that means this has to be n, right? Square root of n times square root of n is just n. So we get, this is actually supposed to be n, like that. And then, so that's interesting, right? So we have n times n, or times the state n, or the state that n describes. So we're calling this a number operator, right? So these two guys bunched in with one another is what's called the number operator. And what's interesting about this, right, is that we did not need to define any new variables, right, if we wanted to get the energy state of, if we wanted to get the eigenvalue of the energy state out, right? Everything is really just in terms of our raising and lowering operators, even this number operator. That's what's super useful about this number operator. We're not going to really touch on it that much in quantum field theory, right? This is kind of just a review before we dive in to quantum, more field stuff, right? So just as a rehash, right? So we went over the harmonic oscillator model again, just a little bit more stuff on the harmonic oscillator, and we came to these conclusions basically, right? We have these things that we sort of arbitrarily defined, right? And we found out that they're related to each other in this way, and that they're related to our harmonic oscillator Hamiltonian in this way, okay? And then we went on and we went to say that we have these relationships here, right? That's sort of what gives us this idea that the way these things sort of intermingle with the real world is by raising and lowering energies. And then when we combine these two things together, we get a number operator, right? We get the actual eigenvalue of the state out of this. What's interesting to note also, before we call it here, what's interesting to note is that this could be a fun exercise, right? We can consider what something like this would look like, or something like that would look like. And maybe I might do a couple of these in the future, right? We can think of these as, okay, say we started in, let's do this one right here. say we start at n equals 2, okay? If we start at n equals 2, looks like we're raising first, then we're lowering, and then we're raising. Okay, so we're gonna get n plus 1 as our state back, right? But then we're gonna have some constant. And what we're gonna find, what you actually find is that the constant is different, right? It could be different when, suppose you take something like this path maybe. So you start again at 2, state 2, and then you go down here, and then you go back up, and back up. So this path might have a different constant in front of it than this path. You start at the same place and you end at the same place, but the path is different. And one way that you can tell the difference between these paths is the constants that you get out of these operators. And I might do something like that in the future, right? And that might be kind of interesting to look at. But that is, I think we're getting close to the end of quantum mechanics review. And we're going to start getting into quantum field theory now, which is, we've come a long ways, right? But the road is still, we're still looking at, we're still on the highway. We're not even close to the end of the highway yet, right? Because once we get open to quantum field theory, there's so many different tributaries of this highway or this river, whatever you want to call it, that we can go down. The quantum field theory is super interesting theory. I can only go over so much, and what I'm doing is I'm going over this book, right? So if you guys aren't aware, this is the book I'm going over, No Nonsense Quantum Field Theory, for right now. And I might go over some more books in the future if that's something you'd want me to do. But anyways, I hope this video finds you well, and I'll see you guys in the next one. Bye.